Hi, I'm Sala, and in this video we are going to discuss decoupling in a static mixing process motivated by this plant, in which, assuming we have some slave flow control loops, we wish to decide how to apportion the level control action nu1 and the concentration control action nu2 to reagent and water flows. In a previous video, first we linearized the static mixing part, the pink block here, and justified that relative gain array recommended this multi-loop pairing. Level was controlled with water and concentration with reagent. Subsequently, in a second video, we proposed this ratio control structure and disregarding the slave valve dynamics. If we linearized the ratio control, we proved that it was equivalent to this multi-loop setup plus some decoupling in inverted form from the level to concentration. Good, so this motivates the idea that, okay, maybe we can do full decoupling. I mean, if we have these pairings selected by our relative gain array, decoupling this effect was done by the formula minus not chosen divided by chosen stuff. So in this case, it is 0.2. But, well, we can also decouple the effect of the concentration loop on the level loop. And in this case, decoupling will be minus 1 divided by 1, so it's minus 1. So somehow, if we put some minus 1 in the block diagram, we will achieve the full inverted form decoupling. So, after the saturation cascade or whatever, the thing we would need to add is this reagent flow, ideally computed by the concentration controller, multiplied just by 1, and subtracted to the level control action. So in this way, in theory at least, we will achieve the perfect inverted form decoupling. So the apparent transfer function after the static mixing will eliminate the non-selective effects. So it will appear like this, in linearized form, from level action to total inflow, and from concentration action to inlet concentration increments, because we are in linearized stuff. So if we were in a linear setup, we would implement this thing here, and we would have finished. Well, okay, there is a parasitic loop here, this 8-shaped stuff that would need to be stable. So depending on the phase lag and times constant of the valves, then we may have some problems. But okay, we will assume that this is not the case. So we will end up this in linearized way. And this would finish the inverted form decoupling. But is there a nonlinear way to do it? Because you know, this block diagram here was the linearization of this ratio control, disregarding valve dynamics. So is there something smarter than the linearized inverted decoupling that generalized ratio control? Well, we kind of have the suggestion from the linear block diagram. The difference between ratio control and the new proposal for decoupling is just adding this green 1 subtraction here. So maybe what we need is just adding this to the block diagram of the pre-existing ratio control. Are we right? Well, okay, in linearized equations, it seems that yes, we do. But let us check it with the nonlinear equations of this block here, again, disregarding this valve dynamics. Which are the nonlinear equations? Well, we have them here. The reagent flow is just the ratio rho times the water flow A. Good. And the second equation is writing this block diagram in here in equation form. So the total water flow A is the sum of three things. Nu1, the level control decision, A zeros, adding it, the operating point, minus the reagent flow. We are disregarding this cascade dynamics. Well, okay, then let us operate on these equations to see what we are finding. We may say that A plus R is Nu1 plus A0, and then R is rho A, so we have 1 plus rho A equal this thing. So if we divide by 1 plus rho, we get this A, and if we multiply by rho, we get this R. So basically, after this static mixing block, total flow will be A plus R, so this 1 plus rho will disappear and will be Nu1 plus A0, and the concentration R divided by A plus R will be rho divided by 1 plus rho. So, what does this mean? Well, indeed we have achieved decoupling in the sense that Nu1, the decision of the level controller, only affects Q, the flow dynamics, and rho, the decision of the concentration controller, well, increment plus operating point, then this rho only affects the inlet concentration, which in due time will affect outlet concentration. So indeed, rho acts on X, Nu1 acts on Q, so there is no crosstalk between these two controllers, and we have achieved perfect decoupling even in the nonlinear setup. So this is good. This means that if we refine the ratio control stuff with this one going back here in sort of inverted decoupling, then the linearization of this is exactly the inverted form decoupling, and operations in nonlinear stuff certify that rho does not influence Q and Nu1 does not influence X. So even in nonlinear, we keep the thing decoupled. So this would end the discussion on the inverted form decoupling. But as we warned that we have this parasitic loop, which if we disregard the cascade stuff, it even would be an algebraic loop, then okay, we may decide that instead of inverted form decoupling, we just wish to do a direct decoupling, in the sense that, okay, if we can somehow manipulate the mixing equations, we can compute the reagent and water flow to fulfill a given total flow and inlet concentration. So, how do we do it? Well, let us think in it in linear way and in nonlinear way. We'll first start by the linear form, because, okay, it's more general. If I have any matrix representation of a linearized model, then the direct decoupling is somehow multiplying the input to my linearized stuff, the static mixing, by the inverse of this matrix, if I wish identity, or well, with some diagonal matrix or whatever, of the desired decoupled behavior. So in a generic case, direct form decoupling is something related to matrix inversion. Indeed, if we operate with this J, inverse of J will give me a decoupler 1 that transforms things to identity, or well, if I wish to have the chosen multiloop pairing gain as a final result, so that my initial multiloop controller need not be retuned, then, well, it's the inverse thing by other thing, by this matrix. So we'll achieve the same thing as the inverted decoupling. But okay, we are not doing the theory here. So let's do it in our particular example and in our particular block diagram. So what we need is that something whose input will be the level and concentration control actions, but well, I changed the order here, I tell you why, because we'll end up being this thing. We are discussing this decoupler 3, which is equal to decoupler 2, and this decide behavior to avoid multi-loop controller retuning. Well, the thing is that this decoupler stuff yields this matrix that I copied here. But the order nu2, nu1 is changed in my MATLAB operations with respect to the order in which this, say, vector appears in the block diagram. So I need to swap columns to implement here in this, let's say, block diagram. So I mean, when you discuss decoupling and Niederlinsky and things like that, the advice is usually that you should put the chosen pairings in the diagonal so that for the matrix inversion and Niederlinsky determinants and whatever give the correct results. I did not do it in some MATLAB operations giving this behavior, and so because of that then I need to switch here. But okay, it's kind of, you can stop and think on it. It's a reordering of things, and as I forgot to reorder the pairings at start, then I need to do it later on, or well, I could just switch the level and controller actions. You know, there is not a single way of expressing multivariable things because reordering of variables is irrelevant from a mathematical perspective. Anyway, if we keep this block diagram, then let us interpret what this means. Well, it means that nu1, the level action, will be multiplied by the first column. So it will apply 1 liter to the reagent flow and 5 liters to the water flow, well, divided by 6, 1/6, 5/6. So it's what we should do to keep the nominal operating point of concentration, but incrementing the total outflow. So the increment, this is linearized, of course, so we need to add later on the operating point, then the increment of flow will be shared 1 to 5 between reagent and water, which is what common sense would tell us to do. So this is good because inverse matrix computation agree with common sense. And indeed the second column would be the column that would share the concentration control decision between reagent and water. And what it says that in order to change concentration but keep level unchanged, keep total flow entering the tanks unchanged, well, then we must increase reagent +5 and decrease water flow -5 in the exact same amount so that the total flow does not change. So indeed, the columns of this matrix, we can build them even from common sense argumentations with no need of modeling, inverting, whatever, Jacobians, linearizations, kind of very elementary thinking about what we are doing will yield me the matrix in this orange block. So this would finish the discussion on the linear direct decoupling. We get some incremental actions, we multiply them by a matrix, and then we add the operating points to give the absolute total reagent and water flow, and we don't have any backwards going blocks as in the inverted form decoupling. But in the same way that this inverse form decoupling was generalized to this nonlinear block diagram with ratio control, we may ask ourselves that, well, is there any way of doing decoupling from the nonlinear equations? And indeed, I left it at the end because it's so easy that if I tell it at the start of the video, you would have stopped watching it because, why do we want to complicate our life when the direct nonlinear decoupling is so straightforward? So let's see the hidden gem on what to do in this static mixing. Well, here we have it. If I have a desired total flow QD and the desired inlet reagent fraction XD, then okay, the equations that are that QD must be R plus A and XD must be R divided by R plus A. And well, basically reagent flow will be the desired total flow times the reagent fraction QD XD, and of course the rest QD 1 minus XD will be the water flow. So implementing those equations would execute the direct, let's say, no backward path, direct for decoupling. So level controller and analysis controller would give me an increment of the desired flow and an increment of the desired reagent fraction. And of course, nonlinear operations need to go back to absolute units and not increments. So we add the operating point and we have the total QD and XD. So carrying out these operations, straightforward ones, then we get the reagent and water flow we need. So when I put this flows to the static mixer, the mixing is like this, so this is the inverse of this, and then I get QD and XD to the level and concentration dynamics of the tank system. So this is perhaps the most straightforward way of achieving the decoupling. No inversion, no ratio control, no nothing. We end up having something that renders all this equal to the identity. So this will be the nonlinear way of doing something that in the linear domain would be a matrix inversion. The thing is that, well, inverting nonlinearities must be done in a case-by-case basis. Maybe it's not so easy. In this case, we were lucky and it was extremely easy, but okay, it may be difficult in a generic case. However, well, in the linear case, it's always the same. Invert a matrix. So, well, you choose. If increments of concentrations are small, then linear stuff will work. And if you wish large level and concentration changes, then maybe you need to resort to the nonlinear options we have examined. Either ratio plus inverse decoupling, or direct decoupling, or whatever. So we will end here, calling that in this video we have discussed the relationship between inverse decoupling in linear case and this extension of the ratio control block. And we have also discussed the idea that matrix inversion stuff in a linear case can also decouple things without inverse going arrows in the block diagram, but we can also do that with these straightforward proportionalities in nonlinear calculations. So once all the options and the relationships among them have been explained, we end the video here. Thanks for watching.